Let's see if we got a few more people. I'm just going to see if we got a few more people. Just for a second. Okay, if you'd be willing to turn on your cameras, I would sincerely appreciate it. And let's jump into this. So like I said this morning, I want to put off the urinalysis lab, the specific lab. Bear with me here just for a second and I'll show what I'm thinking about. I want to put off the lab where you would use the strips for one more week, because I should have explained last week what you needed to do for that lab with the strips, or what you needed to have to do it. And I didn't. And I didn't think about it until after we were done with lab. But what you need to do is, for next week, keep the strips. If you still don't, if you don't have any, if I haven't sent them to you, it's because I don't have your address. And so if you want to participate, I need you to send me your address. As soon as I have your address, I will put them in the mail, and then I'm going to shred your address. I don't keep it around. And so it won't go anywhere outside of my apartment, because I do have a really efficient shredder. But if you'd like to, you have more than enough. You can see I think I sent you 5 strips, and there's only 4 different specimens. I'm not expecting you to do all 4. You can if you like, but you don't need to. And so we will do this next week, but if you would like, because you have 5 strips, you can use the last strip to test your own urine if you want to. The brand of strips are called Q-Test. Q-Test urinalysis strips.
Are we doing like a report on this, or
No,
what's the
you're
assignment?
not. What it is I want you to be able to evaluate. So rather than just this is this and that's what's normal, this is what's not normal and so forth, I want you to actually be able to see it, Lauren. And that's why I sent them to you, is because, you know, with an online
Okay, thank you.
Yeah, with an online class, we spend a lot of time talking about things, and you do some virtual labs, but you don't do a whole lot of hands-on stuff, right? And this is one of those things that's pretty easy hands-on. That's why I'm sending them to you.
I have them for my fish tank, but they're not as in depth.
Oh, really? Okay, that's cool. But yeah, that's why I sent them to you, is just so that you can, it's a lab that's easily hands-on. And so you have 5. You can prepare all 4 of those urine recipes, or you can just prepare 2 or 3 and possibly use the last 2 to test other urine that's not simulated like what we're making where it's homemade. This is the type of strip that I sent to you. And so if you go on Google Images like this right here, you can use this to determine what's normal and what's not normal. What should be found in the urine and what definitely should not be found in the urine. What's a normal specific gravity, what SG means, and what's not normal. And so I'd like to put it off for a week and allow you to give you time to prepare the recipes and make sure you have the ingredients that you need. And do it next week and talk about the results next week. Let's jump into today's lab. And then depending on how much time we have, I want to do a little bit more of the PowerPoint from lecture. So yes, if you still haven't sent me your address, because I know I haven't received everybody's. If you still haven't sent me your address, still feel free to send it to me still. I can tell you I really only have time to be putting things in the mail and making sure that everything gets put out on the weekend. So if I receive it after this Sunday or Saturday, you probably will not be receiving any, because I don't have time to get it in the mail. So the urinary system, some of this will be a review of last week. Some of it will be new. And also this week, there's a urinalysis lab, virtual lab. Plan on doing that. I will send out emails about due dates this weekend. Might be tonight, it might be tomorrow. So urinary system functions in urinalysis. Like I said before, I think I said it last week, the kidneys are something that we take for granted a lot of times until they don't work. And because you can get down to about 3% kidney function before you realize that you have a problem and that you're in kidney failure. They are involved in maintaining your blood volumes, maintaining your electrolytes, maintaining your electrolyte balances, and maintaining your pH and eliminating waste. So look, overview of the functional unit of the kidney, which is the nephron. The renal corpuscle, which contains the glomerulus and the glomerular capsule. The afferent arteriole that's bringing blood into the glomerulus, and the efferent arteriole, which is draining it. The proximal convoluted tubule, proximal convoluted tubule, the nephron loop, which includes the descending limb and the ascending limb, the distal convoluted tubule, and the collecting duct, which is going to drain into the papillary duct, which is going to drain into the papilla, which is going to drain into the minor calyxes, which become the major calyxes, which drain into the renal pelvis and into the ureter, and then into the bladder. Major functions that are going to be occurring here: glomerular filtration, which is going to cause the filtration of and result in a filtrate that's similar to plasma, but lacks blood proteins. There's no erythrocytes in here, and there's no albumin. Hopefully, if there is, that's a sign of a problem. So it's plasma-like filtrate minus all the proteins. After that, there's tubular reabsorption. Many of the solutes that are in the filtrate are going to be removed and returned to the blood. Other substances that were not filtered out in the glomerular capsule or renal corpuscle are going to get introduced into the filtrate. Get secreted into the filtrate. One other thing that we didn't talk about last week is this is where water conservation occurs. So a lot of water is going to be returned, maybe, depending on what our water levels, water homeostasis requires. Water will be removed from the urine and returned to the blood to help with maintain blood volume. So water conservation is going to work to remove water from the urine and return it to the blood and thus concentrate waste. So this, with regards to the first function, the filtration, glomerular filtration rate is crucial. We want to maintain a consistent filtration rate. So the body's always making adjustments to maintain the rate. So glomerular capillary blood pressure is controlled to adjust the rate. If you remember when we talked about the Starling forces in the blood vessels, about the hydrostatic pressure versus the osmotic pressure in the capillaries, and the hydrostatic pressure and the osmotic pressure outside of the capillaries. Those same Starling forces are involved here. We'll spend more time talking about that in lecture next week. But they're also involved here to help maintain the filtration rates. and to maintain the net filtration pressure. So if the filtration rate is too high, reason we keep it consistent, if it's too high, needed substances cannot be reabsorbed quickly enough and are lost in the urine. You don't want it to be too high. You don't want to lose things that you need to be able to reabsorb, because anything, let me back up just a little bit, anything that is not removed from the filtrate and reabsorbed back into the blood and ends up being down here in the collecting duct is going to get excreted as urine. So these four main functions are going to determine what you lose in the urine and what you retain and reabsorb. If the filtration rate is too low, everything gets reabsorbed, including waste that should normally be disposed of. So that's why we keep it consistent. There's three main mechanisms that control the glomerular filtration rates. Renal autoregulation, which is occurring within the kidney. Which includes the myogenic mechanism, the smooth muscle of the arterioles. Tubular glomerular feedback, which we'll talk about in a minute, but it has to do with the distal convoluted tubule and cells around the afferent arterial, modified smooth muscle around the afferent arterial. Neural controls and a hormonal mechanism, the renin-angiotensin system, or RAS, RAS. It's also RAAS, which a lot of times we'll see aldosterone here because angiotensin 2, which is part of this system, works on aldosterone. So the first one, these myogenic mechanisms, tubular feedback, and also the hormonal mechanism, are going to work on the afferent arterial. Remember, afferent meaning incoming, approaching, moving into the glomerulus. Efferent meaning exiting. So that if we constrict, the myogenic mechanism, the tubular glomerular feedback, and the hormonal mechanisms are all acting on the diameter of the afferent arterial. All three of those, actually, all four are working on the afferent arterial. So all of these mechanisms to work on maintaining the glomerular filtration rate are acting on the afferent arterial. Why would that be the case? Why? How would changes to the afferent arterial result in changes to the glomerular filtration rate?
Because it's what's coming in,
Yeah,
what
it's,
what needs to be processed.
it's what's coming in, what the volume is coming in. And so if we adjust, if we lessen the volume coming in by vasoconstricting this arterial, we're going to lessen the blood pressure and lessen the filtration pressure, which is going to lessen how much gets filtered out. Just like Becky said. If vasodilation occurs, it's going to increase the blood pressure because more blood is going to be coming in. That's going to increase the filtration pressure, which is going to increase how much gets filtered. So all just a reiteration, all of these mechanisms are working on that afferent arterial. One thing, let me say really quick, the myogenic mechanism, what that has to do is elastic recoil within the arterial itself. So let's say you have, I have this pen, we're going to pretend this is my arterial. And a big amount of blood just whooshes into the arterial. And as a result, the diameter of the arterial goes like this. All of a sudden, you just let this massive amount of fluid in, aka blood, and it causes a massive expansion of the afferent arterial. As a response to the elasticity within the arterial, it recoils. That's a myogenic mechanism. All it is a massive expanse, and as a response, it constricts. There's a trigger constriction within the muscle. In contrast, the juxtaglomerular apparatus and the tubuloglomerular feedback is going to have to do with the distal convoluted tubule. This is the nephron loop. This is the end of the distal convoluted tubule, where remember how it kind of abuts. Doesn't show it in this diagram. It definitely doesn't show it. But the distal convoluted tubule actually abuts up against the afferent arterial right here. If you remember, I talked about that last week, but it abuts up against it. So this is your distal convoluted tubule. Within the distal convoluted tubule are some specialized cells called the macula densa cells. And when there is an increased amount of sodium chloride in the filtrates, and we'll learn as we talk more about the kidneys, if there's more sodium chloride in the filtrate, there's more water. I'm going to type that out really quick because that's really, 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 really important. And I can tell you that I gave an exam to my physiology students at Stevenson, and there were still students who missed this one. And we've talked about it like probably 20 times. I was not really impressed, but it's all right. So if sodium moves in a way, sodium moves in one direction, whatever direction, whether it moves in or out of a vessel. If it moves into a vessel or space, water, if the membrane of the compartment, bear with me here. If the membrane of the compartment if the membrane separating the two areas to a vessel or workspace, if the membrane separating them is permeable to water, water will follow. This is key. If sodium moves into a vessel, and I'm going to change this just a little bit, and the membrane is permeable to water, water will follow sodium. It will always follow if it's permeable. If it can move through the membrane, when sodium moves through the membrane, if water can move through the membrane also, water will move also. So there's a high, the filtration rate is high. And the result is that there's increased volume of filtrate being produced. And so there's more volume of the filtrate. And the result is that there's increased sodium and chloride in the distal convoluted tubule, which is moving by these macula densa cells as it moves through the nephron. So it moves through the nephron. The macula densa cells, in response to that increased amounts of sodium chloride, because if there's increased amounts of sodium chloride, there's increased amounts of water. Because wherever there's a lot of sodium and chloride, there's most likely going to be a lot of water, because water follows. In response, the macula densa cells are going to secrete ATP. You guys, if Zena probably remembers this better than most students, because she's taking 121 right now. ATP is sometimes a neurotransmitter. So macula densa cells are going to secrete ATP. And mesangial cells, which are in the glomerulus, lining in between the glomerular capillaries, are going to metabolize that ATP into adenosine. And adenosine is going to stimulate granular cells, specialized cells of the afferent arteriole, specialized smooth muscle cells, to constrict, reducing the glomerular filtration rate. Well, let me go through this one more time. So here's the nephron loop. Here's the distal convoluted tubule. When I'm going to recreate this figure a little bit, and I'll mark this. This is the distal convoluted tubule. And remember, it abuts up against the afferent arteriole. Within the distal convoluted tubule, there are some macula densa cells, specialized cells. When the glomerular filtration rate is high, the result is that there's a lot of filtrate being produced. And the filtrate is going to have, if it's, because it's filtrate and has a high volume, it's got a high amount of water. It has a high amount of water, it has a high amount of sodium chloride. So there's increased levels of sodium chloride here. In response, the macula densa cells are going to secrete ATP. ATP is going to diffuse over into the mesangial cells, which are in between the macula densa and the afferent arteriole, and in between the glomerular capillaries. They are going to break down the ATP, converting it to adenosine. Remember, the ATP is adenosine triphosphate. So they're going to remove the phosphate groups. Adenosine is going to stimulate the granular cells, which are specialized smooth muscle cells that are wrapping around the afferent arteriole. The result is that the granular cells are going to constrict, causing the afferent arteriole to constrict, reducing the glomerular filtration rate. Questions? One thing you also see here is, if you remember up here, it said that the other mechanism were neural controls. The sympathetic nervous system also acts on constricting the arteriole. They're working on the granular cells and the smooth muscle of the afferent arteriole. The renin-angiotensin-aldosterone system, in response to a drop in blood pressure because of a reduced, the result, if the blood pressure drops with it moving into the glomerulus, the result is that the glomerular filtration rate will drop. And the kidneys are going to secrete renin in response. Renin is an enzyme that works kind of as a hormone in that it floats around in the bloodstream. And when it floats around in the bloodstream, it's going to eventually run into a molecule called angiotensinogen. The ogen on the end of this, remember, I think we've talked about it. This is an inactive precursor. Anytime that something ends in ogen, it means it's an inactive precursor. So angiotensinogen that's being created by the liver is floating around in the bloodstream, it runs into a renin enzyme, and the renin enzyme cleaves it, making angiotensin 1. Angiotensin 1 starts floating around in the capillaries and eventually, because all the blood ultimately is going to end up in the lungs. So is angiotensin 1. So it's floating around in the bloodstream. It ends up floating up into the lungs, where it runs into an enzyme called the angiotensin converting enzyme, or ACE. We have lots of medicines that work on blood pressure through inhibiting ACE, angiotensin converting enzyme.
I'm sorry to interrupt. Did you say it's inactive or active?
Which one?
The gen, like,
Ogen always means that it's an inactive precursor that's consistently around.
inactive, meaning active, right?
No, I'm sorry. So it's an enzyme. It's an inactive protein, and aka a molecule that is floating around regularly floating around in the bloodstream, like our clotting proteins that we always have a lot of them, but they're inactive until they get activated. So
Okay, okay.
This is one of those. It's always around, but it's inactive until it runs into renin.
Okay, got you. Thank you.
You're welcome. Renin activates it to angiotensin 1. Then angiotensin 1 is now floating around in the bloodstream. And you can see it's significantly shorter because angiotensinogen is 453 amino acids long. Angiotensin 1 is 10. So angiotensin 1's running around in the bloodstream. And because all the blood eventually is going to circulate into the lungs, it runs into an enzyme in the lungs called ACE, or angiotensin converting enzyme. ACE is going to cleave angiotensin 1 to angiotensin 2. Going to take 2 more amino acids off, making angiotensin 2. Angiotensin 2 is now the active molecule. So this is all in response to low blood pressure, which is going to result in low filtration rates and low filtrate being produced. So angiotensin 2 is going to act on the hypothalamus to stimulate the thirst center in the hypothalamus, making you feel thirsty, like you need to drink something. It's going to work on the cardiovascular system to induce vasoconstriction. And it's going to act on the adrenal cortex to make the adrenal cortex secrete aldosterone, which is going to result in sodium reabsorption. If you increase sodium reabsorption, what happens with water?
Increases.
Its reabsorption increases also, because like Becky just said, water always follows sodium. And so the net result of angiotensin 2 working on the hypothalamus, the arterioles vasoconstriction, and the adrenal cortex to secrete aldosterone is that blood pressure gets elevated. Questions? So So we're going to shift gears again here. We're going to talk about transport in the nephron. There's two different types of transport that are occurring within the nephron. We have a basolateral membrane and an apical membrane to all of our epithelial cells. We have transcellular movement through the cells, meaning that things are going to move through the cells. And we have paracellular movement, where things are going to move in between the cells, in between the tight junctions. Things can move in between the cells and transcellularly, primarily due to primary and secondary active transport. I think we've talked about it a couple times, but primary active transport, we talked about it in 121 more than we've talked about it in 122. But primary active transport is this ATP-driven sodium-potassium pump that stores energy by creating a steep concentration for sodium outside of the cell. And then we will let sodium move back into the cell if it drags glucose with it or something else with it against its concentration gradient. So we build up this massive concentration gradient of sodium. And then we say sodium can move back into the cell if it moves something else against its gradient. So it moves glucose from where it's lower out here to where it's higher in here. That's secondary active transport. So the active transport is where we're using ATP directly to build up the sodium concentration. The secondary active transport is we will let sodium move through if it moves something else against its concentration gradient. And you guys, I'm going to stop just for a second because I have a few videos, and first one is this one. I have to find it now, right here. So comparing this primary and secondary active transport.
An animal cell maintains internal ion concentrations that are high in potassium but low in sodium. On the outside of the cell, the concentrations are reversed, high sodium and low potassium.
So inside of the cell, low potassium, outside of the cell, high sodium. And this is maintained by the sodium potassium pump.
Concentration differences represent electrochemical gradients across the membrane, which the cell can later tap for energy. Generally, one would expect such concentration gradients to dissipate, with a net flow of ions moving from a higher concentration on one side of the membrane to a lower concentration on the other. However, a membrane protein called the sodium-potassium pump keeps the ion gradients intact. The ions are actively pumped against their concentration gradients. Primary active transport involves the direct hydrolysis of ATP, which provides the energy required for transport. In the first step of the cycle, 3 sodium ions and 1 ATP molecule bind to the pump. ATP is used to phosphorylate the pump, causing the pump to change shape and deliver the sodium ions to the opposite side of the membrane. At the same time, ion binding sites open up on the extracellular face of the pump. On the extracellular side of the membrane, the pump picks up 2 potassium ions. As the potassium ions bind, the pump releases its inorganic phosphate. The release causes the pump to change shape again and deliver the potassium ions to the inside of the cell, completing the cycle. In secondary active transport, a substance such as glucose is pumped from a region of lower concentration to a region of higher concentration. This process requires energy because glucose molecules are transported against their concentration gradient. The energy that drives glucose across a membrane against its concentration gradient does not come directly from ATP. Rather, it comes from the energy stored in a sodium ion gradient, which was created using ATP. Because ATP does not fuel the pump directly, this process is called secondary active transport. To pump glucose against its concentration gradient, the pump takes up both sodium and glucose from outside of the cell and then changes shape, depositing both substances inside the cell. A pump that transports 2 substances in the same direction is called a symport protein. The sodium ions that enter the cell are later returned to the outside by the action of the sodium-potassium pump. This process, called primary active transport, creates sodium and potassium ion gradients at the expense of ATP.
So do you have any questions? Bear with me just for a second. Okay. So almost all molecules or solutes that are reabsorbed in the proximal convoluted tubule are getting reabsorbed via secondary active transport because of the primary active transport of the sodium concentration gradient. So you keep generating this really high concentration of sodium, and then you let it move through via that transcellular route. If it pulls something along against the other substance's concentration gradient. Other things that move transcellularly paracellularly include chloride and potassium. Things that move via simple diffusion are urea, fat-soluble substances, because they can move through the membranes, and water. This is a diagram that came from your book. So it's kind of the reverse. You have to flip this around. Here's the bloodstream here. Here's the filtrate here. Here's the basolateral membrane. Here's the apical membrane. That's facing the filtrate. To flip it around, because this is the filtrate. This is the basolateral membrane. So what this is showing is that sodium, you've got that sodium potassium pump that's building up this high sodium concentration outside of the cell. and it will allow sodium, it will allow sodium to move back into the cell if it brings other things with it, like glucose, like glucose, hydrogen ions. Actually, hydrogen ions go the opposite way. Glucose, amino acids, glucose, amino acids, other solutes. Some things move via that paracellular route: water, uric acid, sodium, potassium, chloride, magnesium, calcium, and phosphate. Any questions? One thing that we have in the kidney that actually the whole purpose of this, the loop of Henle, remember we had two different types of nephron loops, or two different types of nephrons based on their different loops. We had the cortical nephrons. Actually, you know what? I'm sorry, I'm gonna pause one more time. We're gonna watch the video we watched the last time that I thought was so good. Never hurts to watch it more than once. Right. So talking about the function of the nephron loop.
I think we should explore a few.
Hiya, welcome to Biomed Sessions with me, Ruth. Today we're going to be discussing the function of the nephron. Here we have our nephron, the unit of the kidney responsible mainly for the production of urine in order to get rid of excess water and toxic waste products. There are approximately 1 million nephrons in each kidney. At this end of the nephron, blood enters in via the afferent arteriole, passes through a network of capillaries called the glomerulus, and leaves via the efferent arteriole. As this occurs, components of the blood are filtered out into an area known as the Bowman's capsule. The filtered components, collectively known as glomerular filtrate, pass on into the tubules. Eventually, filtrate enters the last part, the collecting duct, and exits as urine. In men, the kidneys typically produce about 180 litres per day of this filtrate, yet only 1 to 2 litres of urine are produced each day. This means that only 1% of the filtrate manages to leave the nephrons. So what happens to the other?
What happens to the other 99%, guys? And 180 liters of filtrate is produced, and 1.2 liters is approximately what leaves and gets excreted. What happens to the other 99%?
Gets reabsorbed.
Yep. Don't read the bottom here of what she just said, Becky, but I know you saw it.
It doesn't mean that it needs to be
For the most
Say it
part,
again,
filtrate is
Becky, say it again.
if it wasn't leaving the body, then it needs to be reabsorbed. That's my process of elimination.
You're exactly right. Yes.
reabsorbed back into the blood at several locations along the tubule. But how can reabsorption occur? Well, the efferent arteriole doesn't just end there. It branches out to form capillaries which surround the tubules of the nephron. Reabsorption is the movement of substances out of the tubules across the surrounding interstitial fluid into the blood of the capillaries. Now, whilst we're on the topic, we might as well discuss secretion, which occurs in small amounts in the nephron. This is the process whereby substances move from the blood through the interstitial fluid into the tubule. To make things simpler, let's remove the surrounding capillaries and zoom in on the first part of the journey where filtration occurs. I've covered this process in detail in a previous video, which I've linked for you to check out. But basically, most components of the blood, except for blood cells and the majority of proteins, are squeezed out between the pores of the glomerulus to reach the Bowman's capsule. So the glomerular filtrate contains substances such as water, glucose, amino acids, and inorganic ions such as sodium, chloride, potassium, and bicarbonate. It also contains the
Guys, what's bicarbonate?
It's a element? No,
Yeah, what's its purpose?
I do know this. Doesn't it help like acid balance?
It does. What is it? Good job, Claire. What does it do in acid balance?
It makes it more alkaline.
Yes, it's a base. Good job. It's a base.
And
Remember
sodium
that.
bicarbonate
Good
is,
job. What?
Sodium bicarbonate is baking soda.
Yes. Booyah. Yes.
waste products, creatinine and urea. Small amounts of these substances in the blood are okay, but they are harmful in large doses. Hence, the body rids itself of significant amounts via the kidneys. The next destination for the filtrate is the proximal convoluted tubule. Convoluted simply means twisted or coiled. This region is lined with simple cuboidal epithelium, and substances pass from the basolateral surface to the apical surface of the cells and out into the interstitial fluid. Approximately 65% of sodium ions are reabsorbed here through various methods. Positive attracts negative, so naturally wherever sodium ions go, chloride ions follow.
So that's another one. So water, if it's permeable, will always follow sodium. Chloride also will follow sodium. It's a balancing reaction. When we talk about fluid electrolytes, which is coming up after we do the urinary system in lecture, it's going to be a relatively short chapter. A lot of it is going to be a review of what we're talking about right now. Like this. The chloride is going to follow sodium because it balances the charge on the sodium.
Other negative ions do so too. As you may know, NaCl is the formula for common table salt, so it would be pretty salty outside the tubule if it wasn't for the fact that 65% of water leaves by osmosis. In addition, 65%
because water follows sodium.
of potassium is reabsorbed, as well as 90% of bicarbonate ions, which are important in maintaining the pH of the blood. But glucose and amino
So most reabsorption is going to occur in the proximal convoluted tubules.
acids are the champions here, as around 100% are reabsorbed back into the blood to be used in processes such as respiration and making proteins. Note, not all urea leaves the nephron in the urine, as about 50% is reabsorbed. And secretion? Well, ammonia as well as various medications are secreted into the tubule. The next part of the nephron is the loop of Henle, which has a descending limb in which the filtrate travels down, and an ascending limb in which the filtrate travels up. The thin segments of the loop are lined with squamous epithelium. Now, the loop of Henle dips down into a region of the kidney known as the medulla. This region is highly salty. Why? Because sodium is actively pumped out of the thick ascending limb, followed by chloride, but water itself cannot follow because the ascending limb is impermeable to water, hence the interstitial fluid becomes salty. The descending limb, however, is permeable to water, but has very low permeability to ions such as sodium and also urea. So as the filtrate travels down the descending limb, water leaves by osmosis because of the salty environment of the medulla. By the time the filtrate reaches the bottom of the loop, it is highly concentrated as significant amounts of water have left. However, the story is different in the ascending limb, whereby any water that remains cannot escape the filtrate. Sodium chloride, on the other hand, leaves passively.
So the descending limb is descending limb is permeable to water. The ascending limb is not. Sodium is going to get actively pumped into the blood, interstitial tissues surrounding the loop. In the ascending limb, keep this in mind. So we're going to increase the concentration, the salt concentration in the ascending limb. And we're going to learn in the next section that the blood is going to flow this way. What is that going to do to the concentration over here? Keep this in your back of your mind for right now. If we make it really salty and really concentrated as it flows this way, what is that going to do to water movement over here? Don't answer it for the moment.
From the thin ascending limb, then is actively pumped out of the thick ascending limb. After these processes have occurred, the filtrate is dilute. In total, approximately 25% of sodium chloride.
So by the time we're up here in the distal convoluted tube and we poured out all this sodium chloride into the blood, the filtrate up in the distal convoluted tubule is very dilute.
It is reabsorbed from the loop of Henle. In order to avoid cell damage, the amount of water and salts in the blood needs to be kept regulated, and the nephron plays a vital role in this. The distal convoluted tubule, which is made up mostly of simple cuboidal cells, is the place.
So remember, it's very dilute up here, and it's more concentrated out here now. The tissue is more concentrated out here. The blood more concentrated out here. Very dilute in here, lots of water in here, lot less water out here. How is that going to affect osmosis? Don't answer it. Just think about this for right now.
Place where initial adjustments are made to the filtrate. Under the influence of the hormone aldosterone, sodium is reabsorbed.
If sodium is reabsorbed, what happens to water? If sodium, go ahead.
I was gonna say it gets reabsorbed as well because
Right.
sodium follows water.
Right.
Or
Now,
yeah.
Exactly. One thing that I want you to also understand here, and we haven't talked about this, but potassium and hydrogen ions, if sodium gets reabsorbed, potassium gets secreted. Just like we saw with the sodium potassium pump, where sodium keeps pushing it out, but and hydrogen and sodium keeps getting pushed out, potassium keeps getting moved in. It's the same thing here. If sodium gets reabsorbed, potassium gets secreted. If sodium gets reabsorbed, hydrogen ions get secreted. I'm going to stop just for 1 second. I'm going to share something. We'll come back to this. This will make if we get all this stuff down right now, it'll make our discussion of the urinary system in lecture go a lot faster. So here, so sodium, so water follows sodium. Chloride follows sodium. If sodium moves, however, if sodium moves one way, it's pumped one way, potassium and hydrogen ions move the opposite way. So what this means is that if sodium gets reabsorbed, potassium, actually, I'm going to put this on a different line. So what these two things mean all of this right here, what this means is if sodium gets reabsorbed, sodium gets reabsorbed. Potassium gets reabsorbed. Oh, see, wait, not potassium. Chloride gets reabsorbed. And water gets reabsorbed. Vice versa, and vice versa. If sodium gets secreted, chloride and water get secreted. If sodium gets reabsorbed, potassium and hydrogen ions get secreted. Guys, write those things down. It'll help you and I both over the next 2 or 3 weeks. And today. Zena, write it down. Don't just take a picture of it with your phone. Is that what you were doing? Do it, you guys, let me teach you a trick. And I'm realizing with younger students, we're seeing this more and more. If you actually write it down, you'll remember it a lot more than taking a picture of it with your phone. So write it down later because you'll remember it a lot better. The act of doing it will help you significantly.
I agree. I just like to look at it on my phone because I use my phone. a lot.
That works too. That works too. I can tell you how many of my students in my classes, my physiology classes at Stevenson, take pictures of things, but can't remember it for the exam. And it just, I mean, if you know, if I'm writing it out, it's because it's really important. I want you to get it. All right.
Oh, I can relate to your students. Sometimes I'm still, yeah.
All right, let's come back to the video.
Followed closely by chloride, whilst potassium or hydrogen ions are secreted into the tubule. Almost all remaining bicarbonate is reabsorbed, and although the distal tubule is normally impermeable to water, small amounts may be reabsorbed here too. The collecting duct, which is composed of principal and intercalated cells, is where the final adjustments take place before the filtrate leaves as urine. Here, sodium chloride is reabsorbed in addition to urea, although sometimes urea can re-enter the tubule at the loop of Henle in a process known as urea recycling. But what about water? Levels of water in the collecting duct are regulated by the hormone ADH, which acts to retain water in the body by enabling it to be reabsorbed back into the blood.
In order, if you remember, I was saying that, so in order for water to get reabsorbed, when sodium gets reabsorbed, the membrane has to be permeable. The best way to make the membrane permeable is with antidiuretic hormone. So aldosterone will work to reabsorb water by working on sodium if antidiuretic hormone is also present.
Example, if you are dehydrated, ADH allows aquaporins, aka water channels, to be.
The aquaporins is what allows the membrane to become permeable.
Inserted into the epithelium, allowing water to be reabsorbed back into the blood. Remember, the medulla is salty, so if water is given the opportunity to leave, it will. On the other hand, if you're overhydrated, a lack of ADH will mean that the collecting duct is more or less impermeable to water, so excess water can pass out into the urine. In general, urine contains water, urea, sodium, chloride, potassium, and creatinine, as well as other inorganic substances. Okay, hopefully you found this tutorial helpful.
Okay. She does a good job of explaining things. So with the countercurrent multiplier is where the nephron is going to work to concentrate, excuse me, yeah, concentrate the urine. More salt is constantly being added to the filtrate, and therefore the salt is entering the filtrate, going down into the descending limb. The blood is coming in the opposite direction. And it's moving this, rather than moving from left to right, it's moving right to left. Salt is continually being pumped out of the extracellular, so continually being pumped out of the ascending limb into the blood. So as the blood moves around to the descending limb that's now permeable to water, the blood is highly concentrated with salt. So water is going to leave the limb and enter the blood. So the net result of this is to dilute the urine. It's counter current because the filtrate is flowing one direction while the blood is flowing the opposite direction. Because the extracellular fluid is so salty because it's all these ions being actively pumped out over here, by the time it flows over here, the water is passively going to move into the blood. And the more water that leaves the descending limb, the saltier that fluid will be that gets passed over into the ascending limb. So here, the blood is, here's the glomerulus, here's proximal convoluted tubule, here's the descending limb, here's the ascending limb. The blood is flowing in the opposite direction of the filtrate. The salt is being actively pumped out into the blood on the ascending limb. So as the blood flows parallel to the descending limb, it's very concentrated in salt, and the water will passively move into the blood. So the whole purpose of this countercurrent exchange mechanism or multiplier is to result in dilute your filtrate. Now, because I told you I really like the way this person is explaining some things, and so there was another video that she did. I think it's her, we'll find out. And I think we should watch it. So this is talking about this countercurrent multiplier.
If you're in medical school, I can guarantee anatomy is going to be the hardest class to take.
Hiya, welcome to Biomed Sessions with me, Ruse. Today we're going to be discussing the loop of Henle and the way it helps to concentrate urine in the kidneys. The loop of Henle is found between the proximal convoluted tubule and the distal convoluted tubule in the nephron. There are actually two types of nephron in the kidney, cortical and juxtamedullary. This happens to be a juxtamedullary nephron because of its long.
So one thing that I didn't mention, the only place where you find these countercurrent multipliers are in juxtamedullary or medulla. You can see she doesn't pronounce things the way I do. Doesn't mean that we're wrong. It just means we pronounce them slightly different. But she, the only place where you find these countercurrent multipliers are in juxtamedullary medullary nephrons.
Loop of Henle and the fact that it dips down into the medulla of the kidney. This type is well suited to the role of helping to concentrate urine. As discussed in my function of the nephron video, filtrate moves through the tubules and eventually exits the collecting duct as urine. But what we want to know is, why does the concentration of filtrate increase as you go further down the loop of Henle? Osmolarity is the concentration of a solution, often expressed as milliosmoles per liter. Filtrate in the proximal convoluted tubule has an osmolarity of 300 milliosmoles per liter, the same as the surrounding interstitial fluid. This means that the filtrate is isoosmotic with its surroundings, but it's a very different story in the loop of Henle. Let's zoom in. Let me give you a brief recap of what happens here, but if you want more details, including information about permeability, do go back and watch my previous video. Okay, so in the thick ascending limb, sodium ions are pumped out and negative ions such as chloride follow, making the medulla a quite concentrated and salty region. Water leaves passively from the thin descending limb because of the surrounding salty environment, and as the water leaves, the filtrate in the descending limb becomes significantly more concentrated. In addition, the salty medulla is also a major reason why water is able to move passively out of the collecting duct and be reabsorbed back into the blood, thus leaving behind more concentrated urine. But let's pretend that the filtrate is entering the loop of Henle for the very first time. Naturally, because the filtrate is coming from the proximal convoluted tubule, it will have the same 300 milliosmoles per liter osmolarity and be isoosmotic with the interstitial fluid. However, this situation is not ideal for creating concentrated urine. So in the latter part of the loop of Henle, our aim is to create a difference of 200 milliosmol per liter between the ascending limb and the interstitial fluid. The only way to do this is by pumping out sodium ions. So let's pump. As you can see, the osmolarity in the ascending limb has decreased due to a loss of sodium, whereas in the interstitial fluid, it has increased due to a gain in sodium. And if you look closely at the values, you will see that we have achieved the 200 milliosmol per liter difference, otherwise known as a gradient. But what's happening with the descending limb? Here the filtrate needs to equilibrate, meaning that the water will leave passively until the filtrate in the descending limb reaches the same osmolarity as the interstitial fluid. Time to equilibrate. Note, equilibrating does not change the osmolarity of the interstitial fluid. Filtrate moves through the nephron continuously, but I'm going to break this down into steps for you. Let's advance the fluid in the loop of Henle. When brand new 300 milliosmol per liter filtrate enters the descending limb from the proximal convoluted tubule, the filtrate already in the loop of Henle is pushed further along. Bringing back our values for the interstitial fluid, we see that our gradient has been messed up. So we need to re-establish that ideal 200 milliosmol per liter difference. Let's pump out some sodium ions. Okay, although the value is varying, there is still a difference of 200 at all levels, so we're content. Now to equilibrate the descending limb with the interstitial fluid and advance the fluid in the loop of Henle a little. Lo and behold, the gradient is messed up again, but we know what to do. Let's pump and establish that 200 milliosmol per liter gradient. Equilibrate to match osmolarities and advance the fluid. Okay, one more time to get the point across. Our gradient is messed up. Pump out sodium to restore the gradient and equilibrate. All right, so looking at our values for the interstitial fluid, we can see that the osmolarity increases the deeper you go into the medulla. As all that pumping and equilibrating continues.
Guys, what's another word for osmolarity?
Doesn't it mean movement?
You're close. It means something that has an effect on osmotic pressure, like the movement of water, like Claire said. Osmolarity means it's something that cannot pass through the membrane that's affecting water movement because it can't pass through the membrane. Another way to think of osmolarity is a concentration of something that can't pass through the membrane. So the osmolarity is the concentration of the ions within this area.
We eventually reach a maximum concentration of around 1,200.
I am so furious.
What was that? Okay.
The entire process that I have just described is called countercurrent multiplication. Countercurrent because the filtrate flows in opposite directions in the limbs of the loop of Henle, and multiplication because this countercurrent flow enables the effects of the gradient to be increased, i.e. multiplied. So in summary, the loops of Henle of juxtamedullary nephrons are involved in the process of countercurrent multiplication, which enables the interstitial fluid to become more concentrated, i.e. increase in osmolarity going into the medulla. The high concentrations in the medulla facilitate the passive movement of water out of the collecting duct and result in more concentrated urine. Okay, hopefully this tutorial was
Questions?
helpful to you. If
All right, get out of this. So this slide is a summary of the solutes that are reabsorbed and secreted in each region of the renal tubule. So almost all are going to get reabsorbed, and almost anything that needs to be reabsorbed is going to happen in the proximal convoluted tubule. A few things will be secreted in the proximal convoluted tubule. Things that will get reabsorbed and secreted in the, in the ascending limb and descending limb: water and urea, and sodium, potassium, and chloride. In the distal convoluted tubule, sodium chloride, bicarbonate, and water will be reabsorbed. Why do you think we get sodium bicarbonate reabsorbed here? Specifically, we get a lot of it reabsorbed here generally. Why do we get it reabsorbed here? Because it's going to be key in maintaining the acid-base balance. Same thing for hydrogen ions being secreted here. And then potassium and ammonia in the collecting ducts. So principal cells are going to be very important in sodium reabsorption. And so these are what aldosterone focus on. Intercalated cells are going to be involved in reabsorption of bicarbonate or secretion of hydrogen ions in order to maintain that acid-base balance. So hydrogen ions will get secreted by intercalated cells. Have you seen this equation before right here? Write it out a different way.
Okay, how?
It is the same equation as this. Pretend that my equals are arrows going both directions. It's the same thing as, and let me, I'm going to draw it out too. This is the same thing as this, carbon dioxide plus water combines to form bicarbonate, or excuse me, carbonic acid. H2CO3, which then spontaneously breaks down to form bicarbonate. And hydrogen ions. So that same equation. And this all matters because pH, the measure of acidity, is a measure of the free hydrogen ion concentration, or this. Do you see that? So carbon dioxide combines with water to form carbonic acid. Carbonic acid breaks down into bicarbonate and hydrogen ions. The more carbon dioxide you have, the more hydrogen ions you have, meaning the greater your acidity. The more bicarbonate you have, the more carbonic acid you can form. And that will bring down the pH, because the pH is only the measure of the free hydrogen ion concentration. So if you combine them up, the hydrogen ions, They don't measure, they don't get measured into the pH. So looking at this other equation, right here, bicarbonate combines with hydrogen ions to form carbonic acid. Carbonic acid dissociates into carbon dioxide and water. Carbon dioxide diffuses into the cell, combines with water and becomes, right here you don't see it, but carbonic acid, H2CO3. H2CO3 breaks down into bicarbonate and hydrogen ions. The hydrogen ions can get pumped out, and the bicarbonate gets reabsorbed via a chloride shift, where chloride comes in as bicarbonate moves out. That's a hydrogen ion secreting cell. That's the way to bring down the hydrogen ion concentration, by secreting it into the filtrates. The bicarbonate secreting, you can also secrete bicarbonates by combining carbon dioxide with water here, same thing here. It will form carbonic acid. Carbonic acid breaks down into bicarbonate and hydrogen ions. The hydrogen ions get actively pumped into the blood, while the bicarbonate gets secreted. This is going to this process, secreting the hydrogen ions, getting rid of the hydrogen ions into the urine, is going to lower the pH of the urine. Excuse me, yeah, lower the pH of the urine, making it more acidic, therefore making the body more basic. Bicarbonate is going to do the opposite. It's going to make the body, if you secrete bicarbonates, you're going to make the body more acidic because it may have been too basic initially. Is this clear? Questions? Spend some time with that equation, memorize that equation, because we will see it, we see it over and over and over again. So this is that countercurrent multiplier, where we're going to concentrate the urine. When it comes out of the descending limb and then the ascending limb, by the time the filtrate gets up into the distal convoluted tubule, it's very dilute. If you don't reabsorb any water from it, once it comes down into the papillary duct down here, since this is a collecting duct, the papillary duct down here, it's going to be very dilute urine. But if we need to reabsorb more water because our blood volume is dropping, we're going to bear with me here. We are going to reabsorb a lot of that water, producing concentrated urine by adding that antidiuretic hormone, ADH, and reabsorbing a lot of that water. Questions? So one thing that's very important for vitality and life, and you guys, I'm just going to keep going. Bear with me. I know you're probably wearing out. If you feel anything like what I feel like right now, you're wearing out. But please stay with me. Regulating water intake. Your water intake needs to equal your water output. So on a daily basis, the amount of water that you bring in needs to equal what leaves your body. In order to, if for some reason your water intake, you have too much water leaving, being excreted, and not enough coming in, your hypothalamic thirst center will be stimulated. It gets stimulated if the plasma volume, your blood volume, drops below 10 to 15%, or if the plasma increases in concentration, osmolarity. Remember, osmolarity is same thing as concentration. Actually, I'm going to type that in here. It's another one that I'd like you to just remember. Osmolarity is analogous concentration of a solute, of solutes. So osmolarity is analogous to the concentration of solutes. So if the blood volume drops, the osmolarity drops also. Why would that be the case? Why if the volume drops, the amount of plasma volume drops, the osmolarity is going to go up? Someone help me. What do you think? If it's the same thing as concentration, think about, have you ever made, oh, you know what, just. So I am not a coffee drinker. However, I do drink a lot of this stuff, and you can't see what it is. This is the one that I'm using right now because I keep like a 5-year supply of this stuff. And so this is that stuff that you added to water and it gives you caffeine and supposedly some electrolytes and other stuff. You know what I'm referring to. And so
it
it's
like-
highly concentrated, right?
Is it like an
I-
energy?
Yes. Yes. Have you seen these before?
Maybe at like 7-Eleven or something. Yeah.
No, you can buy them at Walmart.
Ah, okay.
I buy them all at Walmart for the most part. So no, these aren't energy shots. These are stuff that you put in some water.
So it doesn't have sugar. It's not like a Red Bull. It's healthier.
I'm not even going to say it's healthier. I'm
Oh.
just going to say, let's not go that direction, because caffeine is definitely not healthy for you overall. But so I have this, and we're going to pretend this isn't a soup cup. Okay. We're going to pretend it's a cup with water in it. And I put some of this in there. And I drink it, and then I set it out in the sun for like 2 days. Whatever was left after I drink what I decided to drink. What's going to happen to it after I set it out in the blazing heat? Let's pretend it's summer and not today where it's just cold.
Well, the water is going to disappear and leave that stuff behind.
Right. So this is going to get much more concentrated. This is going to get more concentrated. Whatever's left in here is going to get more concentrated.
Correct.
That's what this idea is right here. If the volume goes down, the thirst center gets stimulated. But also if the osmolarity increases, aka the concentration increases, the thirst center is going to get stimulated. So they're both going to work on the thirst center. If you increase the concentration, it's going to cause your thirst center to be stimulated. If you increase the volume, plasma volume, if you decrease the plasma volume, you're going to concentrate it at the same time. Do you understand that? Does that make sense? So thirst, that thirst center that gets stimulated is going to get quenched as soon as we drink some water. So feedback signals, moistening of the mucosa, and activation of the stomach and intestinal stretch receptors are going to inhibit make you feel less thirsty. So if you decrease the plasma volume, you decrease the blood pressure, it's going to work on the glomerular cells, which is going to, remember, glomerular cells are going to cause you to secrete renin. I don't think we talked about that, but they will. Those juxtaglomerular cells that are in the distal convoluted tubule are going to force you to secrete renin, which is going to increase the amount of angiotensin II. Angiotensin, excuse me, if you increase the plasma concentration, because you're dropping how much water is in there, so the concentration is going up. You're going to have decreased saliva because you don't have as much water. It's going to stimulate osmoreceptors in the hypothalamus, things that work on water reception, stimulating your hypothalamic thirst center. The hypothalamic thirst center is going to make you feel thirsty. When you drink water, it will moisten your throat and also stretch out your intestines, inhibiting the thirst center and decreasing the concentration because you absorb more water. this helping? Are you understanding? Becky, is it working? Claire?
Yeah.
Yeah.
So regulating water output, obligatory water loss. You have to lose a certain amount of water every day. You have insensible water losses, meaning just evaporation from the skin and the lungs. Water that leaves within the air that you exhale. Water also accompanies undigested food feces in the feces. Also, kidneys have to excrete 900 to 1200 milliosmoles concentrations of solutes to maintain your blood homeostasis. And the urine solutes have to be flushed out in water. How do we regulate water reabsorption? The majority of it is through, well, it's almost all through the hypothalamus and antidiuretic hormone. I can't think of another way that it's reabsorbed. Water reabsorption in the collecting ducts is related to how much antidiuretic hormone is released. If there isn't a lot of antidiuretic hormone to work on water reabsorption from the collecting duct, you're going to produce dilute urine, excrete dilute urine, and have reduced fluid volumes in the body. High antidiuretic levels are going to produce concentrated urine because you're going to be reabsorbing a lot of the water from the filtrate that becomes urine. Hypothalamic osmoreceptors. What are osmoreceptors?
I'm talking and sorry. I'm talking and I realized I was muted.
All right, go ahead. What were you going to say though, Claire? What were you?
Well, I'm like thermoreceptors are detect temperature, chemoreceptors, chemicals, osmoreceptors. It's not coming to me.
Well, what's osmosis? What's
Oh,
osmosis?
movement,
What kind of movement?
diffusion,
Diffusion of what?
water, or a solute.
Water.
Okay.
So these are water receptors. So hypothalamic
No, Claire.
osmoreceptors are going to trigger or inhibit antidiuretic hormone release. Factors that specifically trigger these osmoreceptors include prolonged fever, excessive sweating, vomiting, diarrhea, severe blood loss, or traumatic burns. So things that are going to cause you to lose a lot of water. So if you, excuse me, bear with me here, just for a second. If you increase the concentration, remember osmolarity, let's think of it as concentration. If you increase the osmolarity of a substance, you increase its concentration. If you increase the sodium concentration in the plasma, you're going to stimulate the osmoreceptors in the hypothalamus. Also, if you decrease the blood volume, or the blood pressure, because if you decrease the blood volume, you're going to decrease the blood pressure. Remember, volume is going to cause stretch or pressure. So if you decrease blood volume, you decrease blood pressure. So if you decrease the blood volume and increase the concentration, you're going to trigger baroreceptors in the atrium and the large ventricles. Remember that atrial natriuretic peptide, which is going to stimulate the posterior pituitary to secrete antidiuretic hormone, which acts on the collecting ducts of the kidneys to increase water reabsorption by inserting all those little aquaporins in the collecting duct. And the result is that you decrease the concentration by increasing the volume. And as you increase the plasma blood volume and decrease its concentration because you're increasing the volume, you're going to produce very little urine because you're going to reabsorb most of the water. Trying to think if we should go through all this. I'm trying to think. I'm going to skip through some of this. Last part, talk about acid-base balance. Chemical buffers can tie up excessive acids and bases, but they don't eliminate them from the body. Buffer systems in the body that tie up acids and bases, but they can't eliminate them. The lungs, and you guys, this is related back, this whole acid-base balance is the major thing to remember. Is this equation right here. If you get rid of CO2, the equation keeps going this way, and this gets lower. If you get rid of carbon dioxide, it keeps moving this way because these are all equal, so the reactions both ways are equal. If you get rid of this, you get rid of this. Actually, bear with me here. If you get rid of this, you get rid of this, which is what's making things so acidic. If you increase this, you get rid of this because it will tie it up. It's a base. Memorize this equation. So coming back to this, the way the lungs work on helping you regulate your pH is to work on their only ability to help you regulate your pH is to change your levels of carbon dioxide. If it can drop this, it can drop this. So if you drop carbon dioxide, you drop the amount of free hydrogen ions, making your body more basic. If you increase this, you increase the amount of free hydrogen ions you have, making you more acidic. If you increase the amount of this, you become very basic. If you decrease this, you become more acidic. So your lungs work to change the carbon dioxide levels. Your kidneys work to change the amount of bicarbonate and free hydrogen ions. With this in mind, so lungs can only eliminate bicarbonate by eliminating carbon dioxide. The kidneys can only get rid of metabolic acids and prevent acidosis. So they have to get rid of, they can get rid of bicarbonate, they can get rid of free hydrogen ions. The ultimate acid-base regulatory organs are your kidneys. The kidneys can work by reabsorbing or generating new bicarbonate or by excreting bicarbonate. So get adding more base to your body or getting rid of it. Leo, you cannot be up there. Nobody. No, you can't be up here. Losing a bicarbonate ion is the same as gaining a hydrogen ion because one cancels out the other. Once they combine, because acidity is the hydrogen ion concentration. Leo, don't you dare. Sorry, my cat. Leo. My mom isn't here to keep him entertained also, so he's gonna be more of a pest today. Bicarbonate is, if you have more bicarbonate around, it's gonna tie up the free hydrogen ions. If you tie up the free hydrogen ions, they can't affect the acidity. So if you have more of this around, you have less of this around. If you have more of this around, you have less of this around. Guys, I'm going to stop for a second here. We're going to watch another video. One more. Leo, no. You're going to get locked in the bedroom if you don't stop.
Writing's not that easy, but grammar.
Hopefully.
Hi everyone, a lot of health students have issues with looking at acidosis or alkalosis. This is determining whether the blood is acidic or basic compared to its normal blood pH. Now, there's different types of acidosis and alkalosis. You can have respiratory or you can have metabolic. Now, what I want to talk to you about today is what makes one respiratory-based acidosis alkalosis or metabolic-based acidosis alkalosis. So like I said before, your blood pH needs to sit between the range of 7.35 and 7.45.
So if it's above 7.45, it's too basic. If it's below 7.35, it's too acidic. So acidosis is when it's below 7.35. Alkalosis is when it's above 7.45. And remember that pH is equal to the minus log of the hydrogen ion concentration.
That's the range it needs to sit within. If it goes below this particular range, acidosis. If it goes above this particular range, alkalosis. That's the first point. Next point is when we measure pH, the H simply stands for hydrogen ions. That's all we are measuring in this case. But when we do bloods to have a look, when you get medical professionals taking bloods to have a look at whether somebody has acidosis or alkalosis, they don't just look for the pH, they also look for some other factors to tell them whether it's respiratory or metabolic. Let's take a look. All right, first thing is you must know this equation. The equation is that when you breathe, you produce carbon dioxide. This carbon dioxide will inevitably get into your blood, and blood is filled with water. So when carbon dioxide mixes with water, it produces something. The thing it produces is called carbonic acid, which is H2, there's the H2, C from there, O3, because there's two there and one there. Now, carbonic acid hates itself and splits itself apart, and it produces these two things. It produces bicarbonate ion, and it produces hydrogen ions. Again, when we measure pH, we're just measuring this. So if somebody has acidosis, it means that the quantity or concentration of this is going up, right? If they got alkalosis, the concentration of this is going down. Now, think of this on a seesaw. If you increase carbon dioxide, this goes up and everything falls in this direction, producing more acid. So the more carbon
dioxide, the more hydrogen ions you have.
dioxide, the more acidic. The more acidic, it means it's going down in this direction and the person has acidosis. Usually the body's very good at compensating and it will bind with that and roll back down in this direction and you breathe that carbon dioxide out. All right, let's talk about acidosis, alkalosis, different types. When we look at respiratory-based acidosis, alkalosis, it's looking at this end of the equation. When we look at metabolic, it's looking at this end of the equation. Now, somebody has respiratory acidosis. What happens is it's respiratory based, something to do with breathing. Carbon dioxide is the only thing here that we truly breathe. We do breathe out a little bit of water, but mainly carbon dioxide, right? So if somebody has respiratory acidosis, the carbon dioxide levels must be increasing. Respiratory acidosis, increased carbon dioxide, because this means it binds with the water, produces carbonic acid, splits apart and produces hydrogen ions. This is acidic. That's respiratory acidosis. So what happens with the pH? It goes down, dropping down in this direction. All right, that's respiratory acidosis. What about respiratory alkalosis? Well, it's going in the opposite direction. So in respiratory alkalosis, we're not producing enough CO2. So it's not binding with water, it's not creating carbonic acid, and we're not producing enough hydrogen ions, which means we've just got an overabundance of bicarbonate comparatively, and it becomes more acidotic. So it's a drop in CO2, which results in an increase in the pH. This is respiratory acidosis, respiratory alkalosis. What about metabolic? Metabolic acidosis. Metabolic acidosis is referring to what's happening here. Now think about it. Metabolic acidosis can happen either if you increase the amount of hydrogen ions or if you decrease the amount of bicarbonate, because bicarbonate binds the hydrogen to mop it up and get rid of it. So if that's gone, you're just left with a whole bunch of free hydrogen.
So carbon dioxide is just working on, only affects whether you're got respiratory alkalosis or acidosis. Renal our metabolic acidosis or alkalosis is working on bicarbonate and hydrogen ions.
So when you do the bloods to check for this, in metabolic acidosis, what you'll find is a drop in bicarbonate. This again is if it's uncompensated, and an increase and a drop, in the pH because it's acidosis, so it's going down. In metabolic alkalosis, what's happening is it's producing too many bicarbonate ions, or again, it could be the fact there's not enough hydrogen ions, maybe one or the other. But what we do know is that in alkalosis, there's more bicarbonate ions if it's uncompensated. And what happens is the pH goes up as well. So this is just a very quick run through of what happens in respiratory-based acidosis alkalosis and metabolic-based acidosis alkalosis.
Okay, I think next week, rather than go through another lab, I am going to, I'm gonna catch up in lecture because I think it will help significantly here. And so don't plan on having another lab exercise questions. I think I'd prefer to get caught up in lecture because I think it will help with a lot of this understanding. But let's move forward a little bit more here. We will do the urinalysis because we should finish between lab and lecture next week. Between both periods, both 3-hour periods, we should finish the rest, the pulmonary system and the urinary system. Leo, don't you dare, nobody. So with regards to the kidneys, you can reabsorb bicarbonate or you can excrete it. With regards, and you can reabsorb hydrogen ions or you can secrete them. With regards to the lungs, you can accumulate carbon dioxide if you're too basic to become more acidic, or you can breathe off your carbon dioxide, bringing down your levels of carbon dioxide, making you more acidic. Excuse me, making you more basic. Is this working, Zena? I'm going to wait on the rest of this. I know there's some videos that you can watch during the lab. I'm going to wait on the rest of this. Are there questions about what we've talked about so far today?
No.
Okay, I'm going to stop right here. I want to continue with lecture for a little bit until the end. And then, like I said, next week, I want to have 2 periods of lecture and get caught up with the urinalysis, urinary system, and the pulmonary system. Are there any issues with that? Have any suggestions? Sorry, let's see here. You know what? I want to look and make sure. I'm going to look at, bear with me here, because I want to make sure. I want to make sure that I am right about the lungs' resistance to expansion. Okay, so I'm just double checking because I wanted to know that we were right earlier. Lung compliance is the lungs' resistance to expansion. Leo, no, buddy, you cannot do that. Not right now. No, come on. Sorry, guys. He's being kind of a pain, so he goes over and harasses the one cat that doesn't like him very much.
I have the same problem in my house.
So lung capacities. So residual volume, meaning what's left in the lungs after everything has been after a most forceful expiration. So this is the amount of air that's left in the lungs after someone dies. It doesn't leave the lungs once it's in there. Inspiratory capacity is a tidal volume plus the inspiratory reserve volume. Remember, the inspiratory reserve volume is how much can you breathe in beyond what you would, your normal resting breathing volume. Your functional residual capacity is your expiratory reserve volume. So everything, so You breathe it, you're breathing in tidal volume, breathing in, out, in, out, in, out. Your residual volume is how much do you breathe beyond your, excuse me, your functional residual volume is how much can you breathe out plus any air that's left in your lungs, the residual volume. The vital capacity is the sum of your inspiratory reserve volume, how much can you breathe in maximally, plus what restfully you breathe in, plus how much you can breathe out. So your inspiratory reserve volume, tidal volume, how much do you breathe normally, just restfully? Your inspiratory reserve volume, how much can you breathe in beyond what you restfully breathe in and out? Your expiratory reserve volume, how much do you breathe out beyond your tidal volume? Your functional residual volume is how much is left in your lungs after you've breathed out all that you can. Total lung capacity is all of these summed together. Your vital capacity is your expiratory reserve volume plus your tidal volume plus your inspiratory reserve volume. Your inspiratory reserve volume is your inspiratory reserve volume plus your tidal volume. Your functional residual capacity is your residual volume plus your expiratory reserve volume. And this is just a summary of those. So now some questions. How is the vital capacity calculated?
It's another formula.
What is it?
It's all addition. Hold on. I think it's D.
I think you're right, it's D. Yes. The amount of air in excess of the tidal volume that can be inhaled with maximum effort is what?
B,
Say it again.
B, boy.
B as in boy, inspiratory reserve volume. Yes. Some other terms. Minute ventilation is defined as the total air that's moved in and out of the respiratory system each minute. The tidal volume times the respiratory rate. So minute volume is the tidal volume times the respiratory rate. The rate is how many breaths you take per minute. That, if you remember, we talked about the conducting zone versus the respiratory zone. The conducting zone is where no gas exchange occurs. Gas exchange is going to occur only in the respiratory zone. So the result is that all the air that's filling your conducting zone is an anatomical dead space. No air is exchanged. The physiological dead space is any anatomical dead space, so the air filling up the conducting zone where no gas exchange is occurring, plus any air volume in the alveoli where the gas exchange is not sufficient. So dead space is anywhere where gas exchange is not occurring. Anatomical dead space is any air filling up the conducting zone. The physiological dead space is any space, any space that includes the anatomical dead space and any air space in the alveoli where the gas exchange is less than sufficient. Not normal. It's decreased. Alveolar ventilation is what volume of air is available for gas exchange per minute. So what air is available in the respiratory bronchioles and the alveoli that's available for, that is thus available for gas exchange per minute. Dalton's law is the total pressure of, it is, states, the law states that the sum of all the partial pressures of gas, let me put it this way, air is a combination of several gases: nitrogen gas, oxygen gas, argon gas, neon, methane, helium, krypton, hydrogen, xenon, ozone, carbon dioxide. You probably knew this before you started this class, that it's a combination of all these gases. The total pressure of all of the atmospheric gas on us that is exerted on us is a sum of the partial pressures of each of these gases. So the pressure exerted by each type of gas in a mixture. So the pressure of one gas, let me give you, so at, here, stop for a second. So at the air pressure at sea level is 760 millimeters of mercury. That's the pressure. right? That's the pressure of the air at sea level. And since I can only see Zena, that I'm guessing the rest of you are nodding too. What that means is that the partial pressure of nitrogen, if you look the numbers, the nitrogen gas, the partial pressure of nitrogen gas is 78% of the 760. 78% of 760. I think it's like 597 approximately. The partial pressure of the oxygen gas is approximately 160 or 159. The partial pressure of all the others correspondingly. But when we add up all of the partial pressures of all of the different types of gas of the different gas molecules in the air, altogether, they're going to add up to 760. That's Dalton's law. Questions?
You say the 78% is the 700,
So
the 78% of the 760?
yes. So if you add up, so tell me what's times set, excuse me, 760 times 0.78 is what?
592.8.
So that's the partial pressure of the nitrogen gas. What is it for oxygen? That's 21%. 760 times 0.21 is what?
$150.36.
Okay, so if you take those two, you add them together, we are at approximately, what are we set, 660, maybe a little bit more. It's higher than that. 750.
743.16.
Okay, I'm struggling to do math in my head right now. But yes, so 743, meaning that the rest of the partial pressures are coming from all the other gases. So as you add them all together, the total of all the partial pressures of each gas is going to add up to the total pressure of that gas at that elevation. And if it's at sea level, it's 760 millimeters of mercury. So here's some of the values. Nitrogen gas approximately in the air is 78.6. So its partial pressure is 597. Oxygen is 159. Water is 3.7. Carbon dioxide is 0.3. If you add them together, you're at 760. Once that air reaches the alveoli, because it gets wet, the partial pressures of nitrogen gas and oxygen are going to go down. The concentration, because carbon dioxide is very soluble in water, it's going to go up. And the water pressure, water vapor is going to go up in the lungs. So the sum of all the individual partial pressures of gases equals the total air pressure, 760 millimeters of mercury. When you are at a higher altitude, there's less pressure. There's less atoms of gas. At a lower altitude, there's a higher pressure of gas. That's why people, because you're breathing in lower amounts of oxygen at higher altitudes, this is why people get elevation sickness, altitude sickness. Your body needs to, your body needs to adjust. So the gas composition is the same. It's still 78% nitrogen up here as it is down here. It's just that the pressure is higher down, lower, and lower up. This is a table showing the different partial pressures of oxygen at different elevations. Atmospheric pressure at 0 at sea level is the partial pressure of the air is 159. And the alveoli, because it's wet, is 105. In the alveoli, it's going to diffuse over into the arterial blood and be 100. The altitude at 2000, the atmospheric pressure is 707 millimeters of mercury. When you times that 0.21 by 707, it's 148. It gets wet and becomes 97. When it diffuses over into the blood, it's going to be 92 millimeters of mercury. Since Zena is the only face that I can see here, is this clear?
Yes.
Okay.
Yes.
Liquids will dissolve. Gases will dissolve in liquids in proportion to their partial pressure. Different gases are soluble in liquids differently. So the solubility of gases in liquids differs. Carbon dioxide is much more soluble in liquids than what oxygen is, even though the partial pressures will be the same. This is where we'll start next Friday. We will finish the respiratory system. We will start and hopefully finish the urinary system also. Have a wonderful day, okay? Wonderful weekend.
You too. Thank you.
Thank you, you too.
See ya.
See ya.
Bye.
Bye.
Okay. Is that the end of class?
That's the end.
Okay. See you next week.
Zena, in all honesty, how clear was that?
Hold Hold on a second.
It was clear to me.
Okay. Okay.
Yeah.